Welcome back to Bevy Basics. In this episode, our focus is going to be on expanding the code example. I want you to have hands-on experience building cool things with Bevy. We've covered a lot of theory in the previous videos, and I'd really like to ramp up what we're doing in our code examples. So let's take a sneak peek at what we're going to build today. The spaceship is going to be able to fly around the screen with user input. The user will be able to rotate it with the Control and Shift keys and move it with the WASD keys. The user will be able to fire with spacebar, sending off missiles that fly through space, destroying asteroids. We're going to build all that just in this episode. We're going to also include the logic for collision detection, spawning asteroids, and more. Well, let's go over all the things that we need to cover to get to the point where we can have a spaceship flying around on the screen like we just saw. Here's a quick summary of what we're going to build in this video. We're going to introduce acceleration, and that's going to make movement more realistic. We're going to migrate to using a MovingObjectBundle for components across asteroids, spaceships, and missiles. We're going to start setting up mechanics for spawning asteroids using timers. We're going to generate random positions and motion vectors for these asteroids so that we get dynamic movement. And after we have this, we'll want to make sure that we're not loading the asset for the asteroid every time we spawn one. So we'll abstract our loading logic away into a single plugin that runs on startup. We'll also need to create the movement systems and the input systems to handle firing missiles, rotating the spaceship, and moving it across the screen. We'll also add the collision detection so that when the missiles fly across the screen, we can see if they're in range of an asteroid and despawn that asteroid if so. We'll do that through a central collision detection plugin that will have a generic collider component that we can apply across our different entities. And we'll also have an asteroid-specific behavior for managing what happens when it detects collisions. We'll wrap up by introducing a despawn plugin to optimize the game world, removing faraway entities. Okay, we're about to start coding. Before we do that, though, I want to mention again, GLB Assets, we're downloading these from Polypizza. In this episode and future episodes, we're going to continue to use Quaternius's Ultimate Space Kit. That will be linked in the description. I want to shout out Quaternius for providing these awesome CC0 assets. We're going to use a planet for our asteroid, and we're going to use a bullet pack for our spaceship missiles. Feel free to look around the pack in the Bevy Basics repository. You can clone the repository, and then once you CD into the repository after cloning it, you can just do cargo run -p for package episode 2, and that will run the code for episode 2. Then you can modify the episode 2 code as you follow along here. And once you get to the end of the episode, you should be comparable to what you'll find in the episode 3 folder. That's the complete code. Okay, so let's quickly run our project before we start coding to see where we were in the last video. So we had a spaceship, and it was moving, as you might remember, at a snail's pace across the screen. So let's ramp up our movement capabilities and start making things more interesting. To start, we're going to refactor our movement system. We're going to add a component for acceleration, and we're going to derive, as always, the component trait as well as debug, just in case we want to print this at some point. After that, we'll use the common pattern in Rust of adding constructors for new. We'll generate this with our code editor, so we can just pass in a value for the vec3. Quick physics refresher, remember that velocity refers to the speed of an entity in a specific direction. For example, an asteroid that might be moving across the screen. Acceleration is the rate at which the velocity changes. This will allow asteroids to speed up or slow down over time. Next, we're going to go into our Spaceship plugin and move the Spaceship bundle into movement. We're going to make this a more generally applicable struct. We're going to call it MovingObjectBundle. This way, we can use it across asteroids, missiles, and the spaceship. We're going to add the acceleration component to the bundle and make all the fields in the bundle public so we can use it across multiple files. Then, we'll go back into the spaceship file and import the MovingObjectBundle. Finally, we'll go into the MovingObjectBundle for the spaceship and add the acceleration component. Now that we've added acceleration and imported it to the Spaceship file, everything should compile again. Even though we're not actually using the acceleration component, the Spaceship should still move across the scene in the same way as before. We'll run our code just to show you that everything's still working. Okay, so let's go ahead and put that acceleration into use. We're going to add an update velocity function that takes a mutable query. This query is going to take a tuple as an argument that defines which components it needs to query. In this case, we want a reference to acceleration and a mutable reference to velocity. We'll also want the time resource so that we can know the delta seconds from the last frame. We'll simply loop over all the entities in the query, grabbing the velocity as a mutable reference and the acceleration as a non-mutable reference. We'll then update the velocity's value by acceleration.value, multiplying that by time.delta seconds, the same pattern we used in the previous episode for update position. Finally, we'll want to add that update velocity function to our plugin so that the app runs at every frame. Awesome. Now that we have movement, let's go put that to use by creating a new Asteroids plugin. This Asteroids plugin is going to contain the logic for asteroids moving across the screen, spawning into the world, and later colliding with other entities. So let's get started by importing the Bevy prelude and defining a couple of constants. First, we'll define a constant for the spawn range, both in the X direction and in the Z direction. We'll use the built-in Rust range in order to construct a range of F32s. This range will be related to the camera's perspective. Remember, we spawned the camera 80 units away on the y-axis, and we spawned the spaceship 20 units down on the z-axis. So in this case, having a spawn range for X of -25 to 25 and a spawn range for Z of 0 to 25 keeps the asteroids slightly away from where the spaceship spawns and keeps the asteroids generally spawning in the inner part of the screen. This is arbitrary, and you can feel free to use whatever values you want. Next, we'll add a component for the asteroid. We'll derive component and debug as usual. This component will be just a marker struct. That is, it won't have any data, and we'll just use it to tag entities so we know which entities are asteroids. Next, we'll create a spawn timer resource. This resource will use Bevy's built-in timer. Timer is just a data structure that allows you to tick it and check whether it's finished or not. We can use this to spawn asteroids at a specific interval. Now that we have the required data structures, we can go ahead and start building the spawn asteroid system. Spawn asteroids is going to take the mutable command struct and the timer, which is going to be a res mute of the spawn timer that we just defined. In the body of the function, we'll use the spawn timers field, and we'll tick it with the time.delta. This will take the duration from the last frame and apply it to the timer, essentially keeping track of the time that has elapsed since the last time the timer finished. Then, we'll want to add some logic for randomly spawning asteroids. But in order to do this, we need to bring in the rand crate. Let's go to our cargo toml file and add rand as a dependency. Then, once our code editor pulls in all the dependencies, we can start using rand directly in our asteroids file. Awesome. So now we're going to use the rand crate to generate some random values or vectors for translation, velocity, and acceleration. This will allow asteroids that spawn onto the screen to have random behavior and be more interesting to interact with. We'll first define a translation, which is just a random X and a random Z value from the range and Y of 0. We'll want to confine everything to the Y-axis here so that we don't actually have 3D movement, since we're not going to cover that in this episode. Then we'll define a helper closure that allows us to get a random unit vector in the X and Z directions. We normalize the vectors here so that they have the same magnitude regardless of the randomly generated X and Y values. Next, let's define some constant scalars so we can scale the velocity and the acceleration of our asteroids. After we do that, we'll define velocity and acceleration as a random unit vector scaled by the velocity and acceleration scalars. Then we'll start spawning the moving object bundle into the world. We'll use commands.spawn, passing in the moving object bundle, and filling out the velocity and acceleration fields. Here, we're going to just set the acceleration and velocity to be the random acceleration and velocity that we've defined above. We'll need to import these values or components from the movement file. Then we'll update the scene bundle to use the asset server to load the asteroid that we've already pulled into our project. We'll use transform from translation and give it the provided translation. Finally, we'll want to remember to add the asteroid tag. We already have the collection of components defined by MovingObjectBundle. However, this is not just any moving object, it's an asteroid. So let's tag it with that struct. Great, now our system is doing what we expect. So let's go ahead and add a plugin that integrates this behavior into the app. The plugin will just be a struct, as usual, that implements the plugin tree. The app, in the plugin's build method, will do two things. First, it will insert a resource, a spawn timer. The timer field will be timer from seconds, and we'll define a constant spawn time seconds to define the interval of how often asteroids should spawn. We'll give it timer mode repeating so that this timer continues after it finishes. Next, we'll add systems with just a single system on update. This is the spawn asteroid function that we just defined. Now we can go ahead and add the asteroids plugin to the main file. This way, when we run the app, the system will actually be executed. We should see asteroids spawn on the screen once per second. As we can see, everything's working. As I mentioned earlier, we'll want a unified place where we can load all our assets. Right now, every time an asteroid spawned, that is, every second, we're reloading the asteroid GLB file. In this case, since the file is quite small, it's not a big deal. But in general, this is something you absolutely do not want to do. Instead, let's create a separate plugin called AssetLoader that will store the handles to all our loaded assets so they can be used across all our different systems. In this case, we're going to define a resource called Scene Assets with three fields: Asteroid, Missiles, and Spaceship. These three fields will store the handle to the scene. Then, in our systems, we can just reference that handle to the already loaded assets instead of loading it again with the asset server. As we've done many times before, we'll create an AssetLoaderPlugin and we'll implement the build method. This time, we'll init the resource Scene Assets with its default value. This will just be an empty handle. At this point, we won't want to use it. So we'll need to make sure that all our other systems run after the system that actually initializes the asset. That's going to be run below. We'll run that system one time on startup, and we'll call this system load assets. So let's get started and define the load assets function. Load assets is simply going to take a mutable reference to the scene assets and the asset server. The asset server is the very same asset server we've been using in all our functions to load assets directly. Now, we'll simply instantiate the scene assets struct and mutate it so that that default resource now contains all the handles to the assets that we actually want to load. As I mentioned before, this makes it so all the assets are loaded once, and other systems can simply reference the handles after they're loaded. We're ready to put our asset server to use. We'll go through and update all the places that we previously used asset server directly, and instead reference our scene assets. Get a copy of the handle by cloning it. This will not clone the asset itself, it will just create a reference counted reference to that asset that we can use. We must also change the schedule that load assets executes in. This is a critical adjustment. The load asset system, which initializes our scene assets resource with the actual asset handles, runs during the startup stage. If spawn spaceship were to execute during the same stage, it might attempt to spawn the spaceship before load assets has completed, leading to a potential race condition with uninitialized asset handles. By moving spawn spaceship to post startup, we ensure that it executes only after all startup systems have completed, which includes the asset loading. This guarantees that spawn spaceship has the valid loaded asset handles it needs from seen assets. Now that we've done that, we'll need to make sure to add the AssetLoaderPlugin to our app. We can run the app to double check that all our assets are still being loaded correctly. Great. This is exciting. We now have an extendable, clean method of loading assets that we can use in all our future plugins. So let's move on to movement. We're going to add the ability for the spaceship to be able to move across the screen. In order to do this, we're going to need to handle input from the user. We don't want the spaceship to move randomly like Asteroids. Instead, we want the player to be able to control how the spaceship moves. We'll start by doing a couple things. First, velocity can just start at 0. If the user is not pressing any input, we shouldn't move the spaceship by default. We'll do this by changing velocity to be the vec3 0. Then we'll define a couple constants for the speed, the rotation speed, and the roll speed of the spaceship. These are the 3 different ways that the player will be able to control the spaceship's movement. Next, we'll want to define the spaceship movement controls. In order to do this, we'll need to add a marker component for spaceship. This way we can query specifically for the spaceship entity instead of everything with the transform or everything with the velocity. Let's add that component to our bundle in the spawn spaceship function. Then, let's add a query that queries for all the components we need. In this case, the components that we need are the transform and the velocity. We'll also add a second argument to the query. This will be with spaceship. It will tell the query to only fetch the entities that match both the components that we're querying and the marker component that we've included in the with. We're also going to pull in Bevy's built-in resource for keyboard input. This will allow us to access the key codes that have been pressed on any given frame. We can use the pressed method to check if it's currently pressed, or the just pressed method to check whether it was pressed on this frame. As with other movement systems, we'll also pull in the time resource so we can get the delta time. Let's talk a little bit more about the with argument, since this is the first time we're seeing this. This is specifically useful when you want to query a component, but you don't actually want the data from that component. Instead, you just want to constrain the query by that component to only fetch other components that have that component. This is a very common pattern for marker components when you want to query some type of entity or a specific entity. It's critical to note that the query component takes 2 generic arguments. Both of these arguments can be tuples. If you specify 2 arguments separated with commas without tuples, the second one is the constraints to the query, and the first one is the components. If you want multiple components from a query, you must specify that as a tuple, where each component is separated by a comma. If you want multiple constraints, you will also have a tuple as your second argument with multiple constraints. For example, we could have with x, comma, with y. Now that we understand with in queries, let's write out the function body. Here, we're going to get the mutable transform and the mutable velocity from the query. We're going to use something new here. Instead of iterating over the query, we're going to call .singleMute. This method works when you have a single entity associated with some component. This is a very common pattern to use in addition to with x, so that you can grab some set of components from a single entity that's been tagged with some component. SingleMute will panic if there is not exactly one entity associated with this query. There are non-panicking variants of this function, getSingle and getSingleMute. We're going to define 3 variables: rotation, roll, and movement. These 3 variables will work together to control how the spaceship rotates and moves across the screen. First, we're going to add support for moving the spaceship forward and backward. In order to do this, we're going to check if the user has pressed the S or W keys. S is going to represent backward movement, and W is going to represent forward movement. The next part is very confusing. Velocity's value is going to be updated to be the forward direction that our current transform is facing. However, we must negate this. This is because most assets we find online or on PolyPizza are actually using a different convention than Bevy. That is, the orientation that most 3D models are going to be facing in popular 3D modeling software like Blender is in the positive Z direction. However, Bevy considers forward as the negative Z direction. Thus, in order to make our model face forward by default, we would either need to go into the software and change the direction or negate the forward direction. For this series, since I don't want anyone to worry about needing to know 3D modeling software, we're simply going to negate the forward direction so that our models line up as we expect. However, if you're going to get deeper into game dev, I highly recommend you familiarize yourself with some popular modeling software. Blender is a great free open source option. That way, you can edit your models, change the forward direction so that it aligns with what Bevy considers forward. Transform.forward will give you the forward direction that you would expect. We have our first piece of the Spaceship movement control system written. Let's go ahead and add that to our plugin and run from main to make sure that everything is functioning as expected. We'll see the spaceship spawn into the scene, and we'll also see that we can move the spaceship back and forth with the W and S keys. Right now, nothing else will work and we won't be able to rotate this spaceship. This means that we're currently locked into moving in a straight line up and down. Let's go back to our spaceship file and add 2 new input checks. First, we want to add support for rotation. This check is going to be accomplished by checking whether the user has pressed the D or the A keys. It's going to do so by setting the rotation to be either positive or negative rotation speed times time.delta seconds. We need to multiply by time.delta seconds here so that the spaceship rotates a steady amount per frame. We don't need to do this for movement. The reason for that is that our movement function, which takes this velocity value, already multiplies it by time.delta seconds in the function we wrote before. If we were to multiply this movement value by time.delta seconds, we would essentially be multiplying this value twice. Thus, we leave it off. However, for rotation, we're going to apply this value directly to the transform. Let's also add one more thing. We're going to add roll. This will allow the spaceship to have a visual effect when you press Shift left or Control left. We're going to use the roll speed that we defined earlier to set the roll variable here. Roll is just going to be an effect that's going to rotate the spaceship around the local Z axis. It's not actually going to control the game's movement. Instead, it's just going to allow us to see the spaceship in 3 dimensions. Now that we have values for rotation and roll that can be positive or negative, we need to apply those values to the transform of the spaceship. That way, the model's orientation will change as the user presses the input. We have 2 functions we're going to use here, rotate and rotate local. The difference is this: rotate local takes into account the orientation of the model that's being rotated. That is, it takes into account the transform's existing rotation when applying the new rotation. So here's the thing. Our game may look 3D, but the action is all on a 2D plane, the X and the Z axes. We're keeping it arcade style. So what we're doing here is we're locking our spaceship movement on the Y axis. We're using transform.rotateY to swing the spaceship side to side. This ignores any kind of tilt or roll, keeping it simple. Then transform.rotateLocalZ gives us a sweet barrel roll effect, but since we're in the 2D land, it's purely for show. It doesn't change our gameplay, it just makes everything look cooler, like our spaceship is dodging or banking hard. If we wanted fully immersive 3D movement, we'd need our camera to follow us, and we'd need to change it so that the transform.rotateY was transform.rotateLocalY. This would allow the spaceship to move out of the confines of the X and Z planes. In other words, leaving 0 on the Y-axis far behind it and traveling off into space. For now, we'll leave that for a future video. Now the exciting part. Let's run our code and see our spaceship rotate and fly through space. Here we go. As we can see, we can rotate around the Y-axis, can zoom around in little circles, and there's our roll effect. We're rolling around the local z-axis, and you can see we're rotating around the absolute y-axis. The roll effect, purely cosmetic. It doesn't affect the gameplay when it comes to rotating around the y-axis. Now let's add some weapons to our spaceship. We're going to define a new system, Spaceship Weapon Controls, that also handles player input. But this time, we're going to fire off missiles instead of moving the spaceship. The function is going to take two arguments, commands, and a query. The query is going to query just the transform component of the spaceship. We'll use this so we know how to spawn the missile, and we'll make sure that we tag our query with spaceship like we did before, so that we only get the transform component for the spaceship. We'll say transform is equal to query.single, which just gets the single entity for the spaceship. This is a read-only query instead of single mute, but it does the same thing in that it fetches the single components for that entity or panics. We also need to pull in the keyboard input, just like we did before. And in this case, we'll want to bring in the scene assets since we're going to be spawning a missile into the world in this function. We'll check the keyboard input to see if the user just pressed the key code to fire the missile. In this case, we're binding space to be the input that triggers that. We'll then use command.spawn to put in a bundle. The bundle is going to be the MovingObjectBundle. We're going to reuse this, like I said, across all the different entities in our game. We're going to fill out the velocity and acceleration fields, as well as providing the model. We'll also want to tag this with the spaceship missile component. This is a new component that we'll need to add that will function just like the spaceship and asteroid tags. It won't have any data. It will simply signify to our other queries that this entity is a spaceship. As you can see, this is a common pattern. Since we don't have actual classes in our game, we simply usually tag a collection of components so that we can have a unique entity that can be queried with that component. In terms of the missile's velocity, we want to use the current forward direction of the spaceship so that we shoot it off in the direction the spaceship is facing. Thus, we'll use the spaceship's forward direction, negating it again to take into account the rotation of the model. We'll then multiply that by some scalar so that the spaceship's missile can move at a fast speed. For now, we're going to keep the acceleration as 0, so the missile will just move at a constant speed. We're also going to update the scene bundle to pull in the model. The model's handle will simply be the cloned handle from the scene assets, and its transform will be transformed from translation with the transform of the spaceship offset by the spaceship's forward direction, such that we spawn the missile at the very nose of the spaceship instead of in the center of the spaceship. Finally, we'll go ahead and add constants for the missile's speed and the missile spawn scalar. These are just arbitrary values. Feel free to pick whatever you prefer if you want the missile to spawn farther in front of the ship or you want the missile to move faster. The last thing that we have to do is add the new weapon control system to our plugin. We can then go back to main and run our code. Once everything compiles, we should press space and see missiles flying across the screen. Right now, when they hit the asteroids, nothing happens. This is a bit disappointing, but still a pretty cool effect for the amount of work we put in so far. So let's go ahead and add a collision detection plugin so we can handle things like the missile colliding with an asteroid or the asteroid colliding with a ship. For now, we're going to just implement a naive collision detection system. If you wanted to take this game farther, I would highly recommend upgrading to using a third-party plugin for physics. This is going to be much more efficient and much less tedious. Great options in this space are Bevy Rapier and Bevy XPBD. But let's get started writing our own physics system. Or not really a physics system, just going to do distance-based collision detection. Our collider component will be defined with two fields, a radius signifying how far from the center of that entity that a collision should be detected, and a list of colliding entities. This system, the plugin will set the field colliding entities every frame. Then other systems can check the colliding entities field of whatever entity they're querying to see if a collision happened. This keeps things modular. We can have a separation of concerns between the physics systems and the actual interactions that we want to trigger. Next, we'll implement the new method for collider just to have an easier, less verbose way of constructing it. By default, it will have no colliding entities. Then we'll define a collision detection system. This system will take a query of entities and global transforms. It will also grab the mutable collider component. We use global transform here because if we tag a child with Collider, we don't care about its relative transform to the parent. We care about its global transform in space. Next, let's write out our algorithm for detecting collision. It's going to be very simple and naive. We're going to have a double for loop that's going to walk through all pairs of entities with colliders and check the distance between them. If the distance is less than the radius of collider A added to the radius of collider B, that is, we have an overlap in the collider radius, then we'll insert a new entry to colliding entities. Note, we don't want to consider collisions between entities and themselves. The second phase is going to walk over all the mutable colliders, clearing the colliding entities from the previous frame. Then, if a vector of entities exists in the hash map from our previous phase, we'll go ahead and extend the colliding entities for that collider by the value of that entity list. Next, we'll go ahead and add a collision detection plugin and add our collision detection system to that plugin to run every single frame. Then we'll go ahead and pull the collision detection plugin into our main app and run it to see what's going on. For now, after our code compiles, we'll notice that nothing happens. That's expected because all we're doing right now is setting a list of colliding entities, but we aren't actually doing anything with that yet. So let's go ahead to Asteroids and add some behavior that depends on these collisions. The idea here is to make asteroid-specific behavior when collisions are detected. We're going to pull in mute commands so that we can despawn asteroids upon collision. We're also going to get a query here that queries for entity, collider, and only does the query for asteroids using the with asteroid. In the body of the function, we'll iterate over all the entities and collider components of each asteroid using query.iter. Then we can start running the logic that we want to happen when we detect a collision. However, we need to do something special here to make sure that an asteroid is not colliding with itself. So when we iterate through the collider's colliding entities, we'll check if that colliding entity exists in the query. This is a bit strange, but all it really means is that we're checking if the entity that's stored in the list of colliding entities exists in the query for entities with colliders tagged with asteroids. In other words, all asteroids. Then we don't want to do anything because an asteroid is colliding with another asteroid. It's possible we want some behavior to be defined here for asteroids colliding, but in this case, we're just going to let them fly through each other and not worry about it. However, if an asteroid hits anything else other than a non-asteroid, we're just going to despawn it. This way, if we fire a missile and the missile hits the asteroid, or if the spaceship hits the asteroid, we're going to despawn it. Later, we could also add health and things like that. Note that we're using despawn recursive here. We're doing this because if we only used despawn, the parent would be despawned, but all the children, and remember, for a GLB file, when we spawn an entity, it will spawn with the scene bundle, a hierarchy of entity. So we had a spaceship, it's going to have the entity that we spawned, and then some set of children entity representing the different pieces of the model. And we want to despawn them all at the same time from the scene, thus we use despawn recursive. This is a very common pattern, and you can almost do this by default when despawning things from the world. Next, since we're in the neighborhood, let's add some cool rotation to asteroids. We're going to add a new rotate asteroid function, which queries all the transforms for each asteroid. Then we're going to add some behavior to just rotate the asteroid on the z-axis. This is simple, but it will add some flair to our code so that we'll see the asteroids rotating as we move through space. We'll add a constant for the speed of rotation for the asteroids. We'll also add the systems to our plugin. Now, let's go back to main and run our code. Once everything compiles, we should see the new functionality integrated. When we fire the spaceship, we will see the bullets or missiles flying through space. But wait, nothing's happening. The collisions don't seem to be taking effect. Why is this? Well, you may have noticed, but we forgot to add the collider to any of our entities. This is where bundles come in handy. If we just add a collider field to our bundle, the code will show us every place where we need to insert a collider to our moving object bundle. We can see that we're missing it for asteroids, and we can go ahead and add that with collider new, passing in a radius. Here, we'll just define an arbitrary radius for the asteroids. We won't calculate this based on the model or anything like that. If you use a physics engine and you use colliders with that physics engine, such as Rapier, usually you will use the mesh's geometry to calculate the size of your collider. or you'll approximate it with a bounding box. In our case, we're just picking a number that will kind of work. Now let's jump over to the Spaceship file. We're missing colliders here as well. Let's add one to our Spaceship with collider new. Again, we're just going to pick an arbitrary radius and define that as a constant. We also need to import the collider like before. We'll want to add this same collider to the missile. The only thing that's going to be different is that we're going to specify a different radius, again, a constant called missile radius. We can tweak these numbers to be whatever feels good. For this video, I just picked numbers that will give us a decent approximation for the size of objects in our world. Note that this also shows off the power of bundles and keeping your code organized. Because we use a bundle for moving objects, the compiler can lead us to where we need to make changes in our app. Okay, and now comes the exciting part. We're about to run our app and cross our fingers and hope that collisions work. Well, since this was pre-recorded, I know it's going to work. But for you, I hope it does. We see the missiles flying through the screen, and there we go. We have the asteroids, and they're disappearing. We can also ram our spaceship into the asteroids like a bumper car and see them disappear off the screen. Not exactly realistic, but it's pretty cool behavior if you ask me. So before we sign off for today, we're going to cover one more thing. Right now, we have a ton of entities that we're creating every frame when we fire and every second just as the asteroids spawn. Sometimes they get despawned when they're hit with missiles, but what if they just fly off into space? Do they exist forever? That means things like our collision detection logic would be running on a ton of entities that we don't really care about. Of course, in a more optimized physics engine, we'd probably want to use some spatial data structure to make these computations more efficient. But still, there's a lot of essentially dead entities that are far away that we don't care about. So let's add a despawn plugin that handles the cleanup. At the top of this new file, we're going to add a constant for despawn distance. This is just going to be an arbitrary value, 100, meaning if anything goes 100 units off the screen or 100 units away from the origin, we despawn it. We'll create our plugin just like normal, implementing the plugin tree. In this case, we're going to add to the app one single system that runs on update every frame and despawns faraway entities. Then we'll define the despawn faraway entities system. The system will take the mutable commands so we can do the despawning and a query for all entities with global transform. Then we'll just loop through all the entities and the global transform. We'll calculate the distance just like we did in our collider plugin using the transform translation and then .distance to vec30. This essentially calculates how far away an entity is from the origin or the center of the camera's viewpoint. We'll go back to the main app and we'll add our new plugin. If you run the app, entities should be getting cleaned up now. This won't actually give you any new functionality, but it will make it so that over time, your application won't grind to a halt, something that's very important for a real game. I'll challenge you to find a crash here. Could you think of a way that we could make our application panic? If so, let me know in the comments down below, and I'll let you know if you're correct. And that concludes our video. That was a long one. In the future, I'm going to cover more exciting topics. We're going to dive back into theory. I'm going to talk about things like run conditions, system ordering and system sets, local resources, state, change detection, and more. There's definitely a lot of other powerful features in Bevy. We didn't cover many new concepts in this video. That was intentional. I wanted you to see that what we've learned already forms the foundation for game development. We can build some really powerful things with just this, but there's a lot of neat tips and tricks that can make your code easier to read, more efficient, and once you get to more advanced scenarios, you'll often need those. Otherwise, you'll end up reinventing a lot of patterns yourself. So stay tuned, and I hope to see you all in the next video. In closing, I'd also like to mention the tremendous amount of support and positive comments that we received on the first two videos. I've read through every comment, and I want to thank you all so much for the encouragement. We spend a lot of time creating these videos for you, and the encouragement helps us keep going. I'd also like to mention the very useful Bevy Discord server. If you're building games in Bevy and watching this series, I highly recommend you go join the Discord. There's a ton of really helpful and positive people there. If you have a problem and you need help, it's a great way to just post a thread, get some immediate feedback on what's going wrong. But if you run into issues while trying to follow along with this video, please leave those issues in the comments. And again, thank you for watching.